weeks. And some of you who do not know, Wendelin belongs to, it's not exaggeration to say dynasty, not the dynasty of French probabilists. He was student of Legal, and he was student of Martior, and this group of French group of probability definitely was one of the strongest, or among strongest driving forces in developing probability in second half of past century, and of course many of you ought to know Wendelin's name after the Fields Medal, and I'm not going to talk. You can find nice lectures written by Chuck Newman, Laudatium, or by Harry Kesten for the American Mathematical Society about work, contribution of Wendelin to all development, this spectacular development connected to critical percolation, discovery, and developing techniques related to stochastic Loewner analysis. But Wendelin did very important contributions way before Fields Medal, and all essentially I couldn't find any important prize which you didn't get before. So including Polya Prize, Loev, Fermat, etc. So his contributions and works with Chris Burzi on very fine properties of Brownian motions, and also works with Balentot. Today are playing very important role studying various models, which was continued afterwards picked by Newman and others. So angle which Wendelin attacks topics and probability is very, very broad. So, and today we are going to listen still one more facet of this one was going on here for weeks.
Okay, so of course it's a pleasure to thank Vladas for setting up the school and organizing everything and making sure, that all of us who came from, who didn't know Brazil so well and didn't exactly know what to do at the right moment and how one should behave in the street and not getting robbed and so on, and so and arranging everything with housing and always running around for all sorts of administrative duties for all of us. Okay, I knew Vladas before so very well, so I knew that this is not a surprise for me, but really, he did an absolutely great job during all these weeks, and okay, I would like to thank you very much for that. So, this talk today is somehow strange in a way, because it comes after a school where, I try to convey some ideas and techniques and give details, because that's the idea of a school, to be able not only to see the nice pictures, but also to start putting your fingers into technical aspects. So of course one part of the audience went through these couple of weeks, and the other part, is coming for a colloquium talk, so and doesn't necessarily have the same. So we have clearly two distinct audiences with two distinct backgrounds. With Pierre, we thought it was a good idea still to, speak on a topic which was related to what we have said before, but which could be sort of understood by everybody and independently of the school. So what I will try to focus on is sort of general questions about symmetry and non-symmetry of random curves, and more generally, sort of around us, maybe of random things that we might see around us. And I will, of course, then at some point focus on two-dimensional questions and use some of the results that we derived during the school, but you don't need to understand the sort of the background of these things in order to understand what was going on. So I hope it will be sort of everybody will find some food during the lecture. Also, I'm very happy because it's my last lecture. You know, I like to lecture, I like to teach, but you know, I start, you know, feeling at home in front of this blackboard, and I think it's now time to leave before, you know, you see me lecturing here on Sundays, and it's a very nice room and very nice to lecture here, so I should not do that too much, because otherwise I will not leave. Okay, so maybe I start with a warm-up, which is you may say it's for non-probabilists, but maybe probabilists, it's also always useful, you know, to remember these things from a naive perspective. So suppose that you are looking at a simple random walk in one dimension. So suppose that Sn is what we call a simple random walk in one dimension with parameter p. So p is a number between 0 and 1. And basically at each step, you know, at each step you toss a coin. With probability p you go up, with probability 1 minus p you go down. Right? So you start like this, and you go down and up by a factor, you know, 1 each time. So you do always 45-degree angles. And so basically here you just say Sn is x1 plus xn, and all these guys are independent and identically distributed, and probability to be xi to be plus 1 is going to be p. Okay, so there's, as usually in probability theory, you look at these things, and there's a sort of clear-cut, you know, distinction between what you get, you know, exposed to as supposedly being probability theory in high school or before, you know, just saying, you know, you do that up to 3 times. What's the probability to go up 3 times? It's 1/2 to the power 2 cubed, and so on. And then you feel like it's really poor, you know, conceptually quite poor questions about, you know, enumerating things. And what we are interested in is then say, well, we look at the limit of what happens when n goes to infinity, right? So when we have infinitely many random inputs, and try to understand what structure emerges there. So, of course, sort of what you know is that, if p is 1/2, right? And that's the central limit theorem, that if you take a very large n here, the end value, so the point at which you end up at the end, you know, will sort of the law of Sn over square root of n will be roughly distributed like, you know, a Gaussian random variable. So that's the central limit theorem when n is large. So it's sort of distributed sort of continuously. And you also have what is called local central limit theorem that tells you, roughly speaking, that, you know, the probability that you end up exactly at some point, you know, which is of order square root of n, that this probability will be well approximated by what you believe by the continuous, basically, random variable that would follow the same law. So roughly speaking, the idea is that you are going to be distributed, the value of the endpoint, you know, will be roughly distributed in a fairly smooth way, you know, among the approximately square root of n points that are, you know, the likely ones, roughly speaking. Now, if p is larger, is not equal to 1/2, you know, then you have a bias, right? So at each step, it is a little bit like if you toss a random walk, a fair one, but each time, you know, you have a little bias. Suppose p is larger than 1/2, you have a little bias to go up each time. So when p is not equal to 1/2, you could still, you know, have a sort of limiting theorem. And what you see here is that you can apply the limiting theorem I mean this central limit theorem, to something which is basically, you look at Sn, right, and you subtract the sort of mean value you would expect, right? So unless I'm mistaken, the mean value here will be p times 1 plus 1 minus, okay, so 2p minus 1. So if you subtract something like 2p minus 1 times n, so let's call this mu, the average value of x1, and you divide it by square root of n, then this will be of order again of some Gaussian random variable. Okay, the variance will change slightly, but it will be again sort of distributed in a fairly smooth way. And again, you have some local central limit theorem that will tell you that, roughly speaking, the Sn, will be distributed. We'll choose a point, one of a distance roughly square root of n of this guy, and that's the way it goes. Now, I want to make two little comments. The first little comment is that suppose that I condition, I know I have one piece of information, which is I know that Sn is equal to some number a. I observe that, the endpoint is there. So one thing is for sure is, because each time here during these n steps you go up or you go down, one thing for sure is that there is, some number of upwards, you go a certain number of times upwards, a certain number of times downwards. The sum of these number of times is n, and the difference will be a, because that's the way you end up, right? So if you condition on the n value of your simple random walk, you can ask, okay, conditioning on this n value, what is the distribution of this actual entire curve? If I condition on this, what's the distribution of this? Now, what I just told you is that if you know that Sn is equal to a, each of the candidates, for making a random walk from here to there, has the same number of upwards path and the same number of downwards path, right? And so you know how many there are. It's just a c, the number of times, to choose a certain number of upwards paths are in this possible set of size n. And so therefore, what you get is that all paths that go from, all candidates, from here to there, that end up here will have the same probability of occurring, because their probability of occurring will be p to the power number of upwards, 1 minus p power to the power number of downwards paths. Right? And therefore, if I condition on Sn being equal to a, right, the conditional law on this curve here is just the uniform measure. You choose one among all the possible candidates that ends up at a uniformly at random. Right? They all have the same probability of showing up. And the important thing I want to stress is that this feature does not depend on p at all. Right? Just you don't have to worry about the fact that p is 3/4 or 1/2 or whatever. As soon as you condition Sn to be there, then the conditional law is just a uniform measure among the paths that go from here to there. So in particular, if I take a biased simple random walk, right, sort of with a very strong bias, and I condition it, say, to end up here, and I take a simple random walk and I condition it to end up at the same point, their behavior, statistically will be the same once you condition the end value. So that's one remark I want to make, and I'll come back to that later. The second remark is that, of course, on large scale, if you look at this picture here, when p is not equal to 1/2, then you have clearly two distinct regimes. The first regime will be the one where, okay, I should say one thing, which is very important in everything I'm going to say now, is that the idea will be to let n go to infinity, but to view this sort of curve here in a non-dynamic way. So the idea is to say you fix n. How can I say? Let's look at like this, rather like this. So look at, S and t smaller than 1 over square root of n, for instance. So what I do here is I take this picture here up to time n, and I'm going to rescale time so that this is time 1, and I'm going to rescale, space in such a way that, this becomes of size roughly 1 also. So when you let n go to infinity, the idea is basically that you look at, this long random walk as just, like a long filament, you rescale it, and then you finer and finer. Another way to say is, you take finer and finer grids. So if you look at this, when p is not 1/2, you may have two different things that may happen. Because either, okay, I should say a second thing. There's a very natural thing to do here in that procedure, which is something that we never usually talk about when we teach probability and central limit theorem, is to let p vary with n. Okay. So in other words, for each given n, you look at the law of the random walk, rescaled or non-rescaled, but p may depend on n. So in particular, it's very natural here to take sort of basically p to get sort of closer to 1/2 as n goes to infinity. Why is that? Because if you look at this picture here, you have two possibilities. Maybe, this quantity here, so the basically average deviation that you will collect along your n steps here, maybe it will be much larger than square root of n. Maybe it's smaller. Maybe it's of order square root of n. Right? So the idea is basically if p of n is, minus 1/2, is much smaller than 1 over square root of n. Okay. What is going to happen here in this picture is that this quantity will be roughly Sn over square root of n. Right? So the slight difference between the fact that you're taking simple random walk at p equal 1/2 is simple random walk with a slight bias, you will not see in the end at the scale at which you look at things, because this deviation is so small, that it's basically the same as taking simple random walk. So then nothing happens, you don't see anything interesting. So basically then just Sn over square root of n will still be sort of the same as for p equal 1/2. And now if you suppose that on the contrary, basically Pn, so this is P depending on n, right? So if Pn, is too large, when n goes to infinity, then, the drift, is going to pull you away from distance square root of n of the origin, and then therefore what you see has nothing to do with what you see at equilibrium when p is 1/2, because then NC, this world just drifts away. So in some sense, it doesn't converge to anything, it becomes very large. And of course now there's an interesting, a natural feature that happens when p minus 1/2 is of order, say, constant over square root of n. Right? So basically what you have here is that at each step, you have a long random walk of length n, but at each step, instead of tossing a fair coin, you toss a slightly biased coin, of order, where the bias is of order 1 over square root of n. Well, in that case, it's very clear what's going to happen. Then what you end up here is, on the one hand, the fact that, which is not surprising because of the renormalization that you're using, that the limit of this s n t over square root of n, when n goes to infinity, you know, as a function here, this converges to a Brownian motion with drift, with constant drift. So in other words, you know, the guy with the fair coin would be just, in the limit, a Brownian motion. And the guy with this type of biased coin here, in the limit, you know, it would be a Brownian motion that is drifting upwards. You know, so this will be bt plus some constant time t. So let's just take t. Okay. So let us try to combine sort of the different remarks that we had before. What we see here is that when, you know, mu is of order 1 over square root of n, the drift, you know, that you are going to collect will, you know, push you away by some quantity which is of order square root of n. Right? And so, so basically, what this guy is doing, you know, if you look at the value at time n, is choosing a point at random, you know, as the endpoint. But this point at random will be, again, still sort of fairly smoothly distributed among points that are roughly a distant square root of n of the origin. Right? Because it's constant times square root of n plus this deviation, which is also of order square root of n. So this guy and this guy, if you look at the value of their endpoints, right, there will be the law will be different, but they will be absolutely continuous with respect to each other, because basically in both cases you're going to choose some point, you know, some random point at distance square root of n of the origin, and which is fairly smoothly distributed. Now, in the limit of this guy and of this guy converge to these two quantities, which is Brownian motion and Brownian motion with drift. And so the following is then going to be true, because it's just, you know, the discrete observation I did before passing to the limit, that this guy, what you do, one way to view this guy is to say, well, I first choose the value, I mean the endpoint. This is distributed according to a Gaussian random variable. And then, you know, the law of the curve from here to here is what we call a Brownian bridge, you know, a Brownian motion conditioned to go from here to there, which is the scaling limit of the uniform distribution among the, you know, zigzag paths that go from here to there. Now this guy here, again, you know, chooses, if you just look at it constructed in that way, you can first choose this guy. You choose the endpoint, which is again distributed according to some Gaussian random variable, except that it is sort of, the mean is shifted by a factor of 1. And then once you have chosen this point, you know, this curve is just the same Brownian bridge as we had before. So what I'm aiming at is sort of, you know, a sort of a hand-waving proof. Of course, if you know Gaussian spaces or something, this should, what I'm saying here is more or less trivial, so I'm not saying anything deep. But I'm just saying that if I show you a trajectory like this, right, which is a Brownian motion, you will not be able to tell me by looking at this picture, you know, whether this is a sample of bt or bt plus t or bt plus 5 times t or bt minus 5 times t, because the law, you know, the distribution of bt or the distribution of bt plus t, you know, as a function up to time 1, they are absolutely continuous with respect to each other. Right? So if I sample a Brownian motion with drift, or if I sample a Brownian motion, you don't see any difference. You know, they are both probability distribution which have the same support. So you're just choosing among the same, you know, you have slight difference. The slight difference is just due to the fact that the distribution of the endpoint is slightly different. But once you chose the endpoint, the law of the curve is just, the distribution of the curve is the same. So let us just sort of, I want to make two little comments because, you know, this is important. You know, this is a toy model that is going to be useful later on. So the first comment I want to make is that in some sense, you know, you may say that this model of a simple random walk, if you don't like, you know, the dynamics of a simple random walk, you might just say, well, you know, this is just an interface. You know, imagine that here you have a one-dimensional, it's a one-dimensional interface. Here you have, you know, some phase here, and here you have some other phase here, and you know that the you know, the line that separates these two things is has to be, you know, a broken line like this. And so imagine here you have everything is yellow, here everything is white, and you have the separation line that separates the two. Now you may say, well, you know, white in some sense, you know, is stronger than yellow, so that if you look at this picture from here to there, that, you know, maybe the interface has a tendency to go up, because somehow the pressure from here, you know, is stronger, or whatever you want to model it by. So it's clear that you're going to see, you know, different phenomena. Sort of basically, either you are at equilibrium, right? So both have the same strength, and you have a simple random walk converges to Brownian motion at large scale. And then if you start, you know, making that things are not even, so that, you know, white is in better shape, then the thing will go up slightly. You know, you start pushing it upwards, but still what you will observe, sort of the interface will still be, you know, the local properties of the interface and will not be distinguishable from the initial one. So the slightly, you know, off equilibrium phase, which is what you see when you have putting a slight drift here, is not the same, is still looks the same, exactly the same as at equilibrium. And then, you know, if you go, if it's I mean, if there's no sort of, I mean, if Pn, you know, minus 1/2 is larger than 1 over square root of n, basically, you know, everything explodes in some way, and sort of this will become like this, and you don't have any phase transition anymore, you don't have any interface anymore. So the idea, you know, you start pushing, you know, making games uneven in that picture, then you still see the same type of things when you are slightly off balance. Okay, that's the first remark I want to make. And the second remark I want to make is one way to understand what is going on here it goes as follows. So suppose I have a Brownian motion with drift 1, right, up to time 1. So this is the law of bt plus t. Right? And suppose you divide it into two pieces. You just say, well, I look at what happens up to time 1/2, and I look at what happens between time 1/2 and time 1. Right? So what you have to do in order to get from here, so what sort of curve do you have here? You have two independent pieces, the green one and the yellow one. And you might say, well, I mean, the yellow one, you know, is still, you know, still a Brownian motion with drift in some way. So what you're going to do is you're going to take the yellow one and rescale the yellow one in order to get a Brownian motion up to time 1. So you blow it up, you know, by a factor of 2 here, and you blow it up by a factor of square root of 2 here. This is what you have to do in order to recreate, that things have the right scale. And what you end up here is a Brownian motion up to time 1 that you obtain just by, you know, zooming in by a certain factor the first part of your initial Brownian motion. Now, if the initial guy was a Brownian motion with drift t, then this guy where you zoom in things, you see that here you have to multiply time by 2 and space by square root of 2. So the drift of this guy here will be now not, you know, so this will be a Brownian motion beta t plus, and now it's t over square root of 2 that you get here. You know, so basically if I take the first piece here and zoom in, and I look, what you see is that the drift that you observe here, if you have to rescale and view these as, you know, define the drift gets smaller. So in particular, of course, if you, you know, divide these curves into, you know, plenty of independent little pieces, what is going to happen is that your initial drift, the initial off balance, the more you zoom into the curve, the less you see it. Right? And so that's exactly the idea that is telling you, because if I take a very small piece, and if I could detect, that there is a small drift here, I would not, be able to by collecting all this information and averaging out these little pieces of information along the path, maybe, I could say, well, I know there's a drift upwards or downwards because on each small thing I observe something special. But here the entire thing, the story is precisely that the more you zoom in the thing, the more, the more the information about the drift disappears. So that's just a simple. Okay, so this was just, a very short, or maybe not so short, but a little warm-up to have you started with the type of questions we're going to ask. Okay, so now there's, say, a first model, which is in some way the natural thing you want to do if you start playing with this idea that these guys are interfaces between two domains, white and yellow, and try to understand, competition between two different domains. And of course, here there was an assumption which was not so clear. Why has the interface between white and yellow has to go, like from left to right? Why can't it turn like this? So the first model that you look at, which is this. Okay, there are plenty of models that you could define, but all of them will naturally have a feature, which is that that a domain, stability of a domain, or the definition of a domain, or the pressure in the domain is somehow made out of the small infinitesimal building blocks, and things evolve locally. So if you are doing statistical physics, you're just saying you're looking at a model with nearest neighbor interaction. That's how we call them. And the simplest one is the one where there's no interaction at all, which is the one that Pierre has been talking about, which is percolation. So the simplest model is, okay, what colors did I use there? Blue, no, yellow, and, okay, let's do blue and yellow, and our Swedish friends will be happy. So suppose that you have a domain here where everything is blue here, here everything is yellow, and in some sense, they are fighting for space, and they're fighting, to trying to invade the domain, with these two boundaries. So the percolation model, the natural percolation model, is to, you divide this because of you learn in school that triangulations are nice, and therefore that or you learn by looking at bees or whatever that this is a natural thing to do. So you take a hexagonal lattice here, with hexagonal sides here, and a small, our mesh size will be delta, we'll see that later. And basically each cell, so this is the percolation picture, but you could try to do similar things with easing or whatever for those of you who've been to this. You have a parameter P, again, and each cell is going to toss a coin and to decide with probability P to be yellow or blue. So here, blue, blue, yellow, yellow, and so on. Now, there is a, so for those of you who see, remember the pictures that Pierre has been showing before, you see that this is the low-tech version of the nice large-scale pictures, on the computer that Pierre has been showing, and that once you did this, there's a very natural curve that you want to draw, which is basically the curve that is going to separate, the set of yellow cells that are connected to the bottom part from the set of blue cells that are connected to the top part. So basically, what this orange curve is doing, and those who have been following this the course know that, of course, have seen that, basically in each of our lectures, that this orange curve is basically, the one that is making its way, in between, leaving yellow to the right and blue to the left, and making its way through this labyrinth. And this is well defined because you are looking exactly at hexagonal cells, so that these curves can always be well defined. Each time you hit a new crossing, you turn right or left just depending on the color of the cell you bump into to decide if you have to go around it to the left or to the right, and then eventually you'll end up to the other side. Okay, so you can view this sort of orange curve in some sense as the interface or the frontier between some yellow domain, and some blue one. They are fighting for space, and they do it at random, and that's the random curve, separation line that appears. Of course, here inside here, you may have, blue cells again, so it's not as simple as that. But that's one natural way to define, a random interface like this. Another way would be, to do it, which is also maybe more physical. And if you want to view this as an interface, if you view it in a dynamic way, is to say, well, I start from here. Here I have blue. Here I have yellow. And, I start to go from here. I discover, here I have here I have a blue hexagon. Here I have a yellow one. Okay? And so blue and yellow are going to fight. And each time they discover a new hexagon, either blue is going to win with probability p, or yellow will win with probability 1 minus p, and so they will decide. And so, which means that, blue wants to turn right, yellow wants to turn left, and each time you discover a new hexagon, you toss a coin to decide whether you turn right or left. So here, clearly, so for instance, if this one is discovered to be blue, which happens with probability p, then you have to turn right. Now, this one is discovered to be yellow, you have to turn left, and so on. Okay. And many times it will happen that you are going to discover a hexagon that you have already colored, that has already been fought for before, and then, you have to turn into the direction which is given by this color. So in particular, okay, we will come back to that later. So, now when delta, so what percolation theory tells you and what people in the course, have been learning is that if you take p equal 1/2 and you let delta go to 0, then the law of this, orange curve is going to converge to some continuous curve, a little bit like simple random walk converges to Brownian motion, and that this, random curve is what we call an SLE curve. So anyway, it's some random curve like this. And there's one observation that I will come back to later, that some features, here this orange curve is clearly a frontier between two simply connected domains, because they are, boundaries of these yellow guys to the right and blue guys to the left. But here in the limit, maybe here, imagine that here from time to time you, on the lattice scale, you had a picture where here you had a yellow balloon attached to this single guy here, and that everything outside here was blue, and that you were continue like this. Okay. So in the discrete case, you may have an interface that does this, and then the limit when delta goes to 0, this mesh size, this is of size of the mesh, and goes to 0, so that in the limit, the picture, could have, fjords that, close up. And so this picture is still, frontier between a yellow domain and a blue domain, but here basically, the yellow part, is able to go through this point, even though the blue one is able to go through these guys and to touch here to here, right? So in some sense, you have this sort of a interpenetration of the blue and the yellow things. right? So the yellow one may have holes inside it. Okay, but this is very clear. So blue, can go through. It can happen that blue goes through fjords like this. Okay, so then of course by definition, like Brownian motion is upwards, downwards, symmetric. Up and down play the same role. Here, clearly, this orange curve, because p is 1/2, is more or less is symmetric in whatever way you want to define it. So that if I show you, a little piece of the curve, of this orange curve that you get here, you will not be able to know, whether yellow was to the right or whether it was blue to the right or could have appeared in both directions. In the same way that if I give you a Brownian motion, well, it's upwards and downwards symmetric, so you don't know. If I show you a Brownian motion, you will not be able to tell me if this is or minus the Brownian motion. Right? The Brownian motion and minus the Brownian motion have the same law here. In the same way, this scaling limit when p equal 1/2 is symmetric. Okay, so as Pierre was explaining in his lecture, when you try now to push p slightly away from 1/2, what happens? If things are unbalanced, what is going to happen here? So basically, the same, three cases will reappear in this case. So the first case is if Pn, minus 1/2 is too small. So here I should say P delta because the number of steps is not really fixed. It's the lattice size that is going to 0. So if P of delta is going to 0 and is too small in some sense, then basically what you are going to observe is the same as the picture as for P equal 1/2. You don't off this. It's too close to the tied game, so it's still the same picture on the large scale. So it's just the same. Now, if P delta minus 1/2 is too large, well, then what is going to happen is that basically blue is going to invade everything, or yellow is going to invade everything, depending if P is larger than 1/2 or not. So what's going to happen here is if this is too large, then the interface will not do anything interesting. It will just, for instance, do in the limit, go like this. Because one of the colors invades everything. This is a supercritical regime that Pierre was talking about. And now the question is sort of if P, there is of course at some point, you have to go from this regime to that regime, and what happens there? And so when P delta minus 1/2 has the right scaling, and so now I will cheat and explain you why I'm cheating, but I'm going to cheat consistently the same way during the lecture. So. Because I think it's easier to explain. If you suppose that this is like constant over n to the 3/4, that's what you have to, delta to the 3/4. So that's what you have to push it away from off balance in order to make it work. Then what you will see is indeed a random curve that goes from here to here, when delta is very small, and so which tends to be of course, lower than the one at P equal 1/2, for instance, if you have more blue than yellow, but which still, doesn't look like that. You still have some orange curve here that sort of stays away from the lower part, or at least doesn't glide along the lower part. But is still not the same as the one at P equal 1/2. So why did I say that I cheated here? Because the right way to express this quantity is not constant times delta to the 3/4. The right way is to express this right off balance that you need in terms of probability. It's actually sort of a 4-arm exponents. It sort of should be expressed in terms of a 4-arm event that I'm not going to describe. Pierre has described them before. And so basically what we know, and this, so that the right thing here is actually, so that's for those who follow the course, would be sort of a 4-arm event, from delta to 1 times n squared, or times delta squared. So basically, and we know that this quantity is comparable to this plus little o of 1 here, so that's why I'm cheating. So there exists some right order of magnitude that we know is comparable, roughly speaking, to delta to the 3/4, but not exactly. We don't control it well enough to say that it's constant time delta to the 3/4. But let's just, to fix ideas, say that pretend it's delta to the 3/4 and not worry about that later. But each time I will quote something like delta to the 3/4, there will be a slight unprecision, something which is not precise there behind the scene. Okay. So now we just raised the question about, what happens to such a curve that you have here. Okay, maybe I should explain just a little bit, where this delta to the 3/4 come from in order for you to see, where the 4-arm type stories come in still. So suppose that you start with a picture at p equal 1/2. So you start with a percolation picture where, each hexagon has a probability to be 1/2 to be blue and 1/2 to be yellow. So what you have is a sort of an interface here. And then, in a way, you're going to couple the realization at p equal 1/2 and the realization slightly away from 1/2 in a way that you're just, like if you heat slightly the system, some of the white guys will become blue, right? Some randomly chosen yellow guys, will become blue, and in that way, the picture you see at that moment will be the percolation with parameter, which is not 1/2, but slightly off that. So, typically speaking, on large scale, when some cell becomes, if I look at this cell, which is yellow, and if it now becomes blue, you are asking the question whether the curve gamma, what will happen to the interface gamma for that cell. So the point is that if you want gamma, to change, because you change the color of the cell, the first thing, of course, is that gamma had to go, that this cell had to be on the neighborhood of gamma of this interface, because otherwise you never have to use this color to decide where the interface actually is. So you have to go through it. So which means that here you need to have, a path, this one should be connected to the top by a blue path, this should be connected to the bottom by a yellow path, because otherwise you will never, reach this cell. The curve gamma will not go through there. Now, the question is now, when this one becomes blue, maybe the interface is just, instead of coming from far away all the way here, and instead of, going like this, maybe it will just, go like this, and just do a little difference, have a slightly different behavior, but this will still be, the difference between the two would be microscopic. So if you want, the curve gamma to really change by the change, or being affected by this change of yellow to blue, this guy here has to be really very special in the sense that the curve gamma, once it did hit this guy, should maybe go like this instead of like this, and this should be sort of a macroscopic size. So if this happens, that means that here, you should have a yellow guy here that pushes this guy up, and you have a blue guy here that pushes that guy down. Okay. So basically, what you need is to look at the following picture. At p equal 1/2, roughly speaking, you need to look at, the special cells, that are in some sense pivotal so that here I have blue, blue, yellow, and yellow here. You should detect such guys. And then the curve gamma will have to go through there. And if you flip this guy from yellow to blue, then, you will have a macroscopic difference in gamma. And somehow the general philosophy of what about Kesten scaling relation and near-critical studies that Pierre was talking about is precisely, lies in this idea that this is exactly the procedure that is going to put you off balance first. That when you slightly change P from 1/2, first nothing happens, and things start to happen exactly because at some point you start hitting such points. So when do you hit such points? Well, when P minus 1/2 becomes comparable to basically 1 over this number of such points. Because, if you have, say, 1,000 points, each one has a probability 1 over 1,000 to be hit, then, you have a certain positive probability to actually hit one of them. So you need one. So how many such points are there? Well, these points will be, so delta minus 2 is the number of points. Right? And for each given point, in average, for each given point, what's the probability that it is like this? Then this is the probability of a, locally here, you need a 4-arm event, so a configuration with a star-shaped things that goes out of here. And this is stuff we computed in the lectures, which is delta to the 5/4 plus little o of 1. Okay, so now we push, we do this slightly off-balance picture, and we are precisely there in the regime that, Pierre was talking about, saying, you are in this, when he was looking at gradient percolation, when you are in this strip, that's precisely when you are, floating, when P is floating between, in taking one of these values where things are slightly off balance, but not too much. Okay, so how can I explain things? So there are there are several statements that you can make about this off-critical case. The first one, which is basically what physicists tell you, and what you can prove, and what Pierre has recalled also, is that the global properties, some global properties of these orange curves are still the same as at criticality. So, for instance, one thing we cannot prove, for instance, at the moment, is the fact that when delta goes to 0, the law of this orange curve converges to some limit if you take P slightly off critical. What we can prove is that this family of probability measures is tight, and so that any, if I take any delta n going to 0, I can find a subsequence such that the law of the curve, corresponding curve, converges. So there are these tightness type issues, but we cannot really prove at the moment. Probably some arguments developed by Odette Schramm with Christophe Garbon and Gabor Pete will work and will show indeed that the scaling limit is unique. But actually for the question we're looking at, this is not really relevant, because we can just say, well, let's take any delta n going to 0 such that the law of the curve converges. So when delta n goes to 0, the law of this interface, which is slightly off-balanced, is going to converge to the law of a random curve. Now, you may say, okay, what can we say about this random curve? Well, what physicists tell us that basically this belongs to the same universality class. That's why they say as the critical case. And so they expect, and this is what Pierre was using, in fact, that the critical exponents that appear, so 4-arm events and things like that, are still, if in the off-critical case and at the critical point, they are still comparable. So what you get is, for instance, that this curve here at criticality, which is this SLE curve that we saw, can be proved that the dimension of this curve is 7/4, almost surely, when you are at p equal 1/2 and let delta go to 0. And what you can prove here is that the off-critical guy, for instance, will still be of dimension 7/4. You know, still have the same type of roughness than the initial guy. And many things are the same. In particular, any correlation functions that's in the physicist language that you can compute for the off-critical case and for the critical case, and that's what physicists had been doing using conformal field theory, are basically, you know, comparable up to constants from the off-critical case than from the critical case. So, in some sense, the finite dimensional distributions of these two curves at the critical point and near the critical point are the same. Okay. So, but still, there's the question, you know, if I show you a little piece of this off-critical guy, you know, is it symmetric or not? Is there something that remains visible? Is there a intrinsic difference or not? So in other words, is the measure of the critical interface absolutely continuous with respect to the measure of the off-critical one, or are they actually living, you know, in some complete disjoint spaces of curves? And the answer, somehow surprisingly, maybe for the physicist, or some physicists, is that the off-critical, we're going much slower than what I thought, interface is not symmetric. So, in other words, if I take a scaling limit of a guy which is off-balanced, the measure here and the measure there become singular with respect to each other. So the situation is completely different than in the simple random walk we had before. You know, now we push slightly so that the curve is different, you know, is not, and as soon as you push a little bit so that the curve becomes slightly different, the curve itself is completely different, you know. So off-critical interfaces, so, and critical interfaces live on different spaces. Okay. So let me just explain why this is true, and then intuitively sort of what the intuitive idea is, because it is going to be important to understand what I want to say afterwards. So I just said that the curve has a dimension 7/4. Right? So roughly speaking, if I'm taking a very small delta, okay, I shouldn't say. So let us look already at this curve in the limit, you know, the continuous curves. It has dimension 7/4. That will mean that, you know, if I take a small delta, it will meet approximatively sort of eta to the minus 7/4 small balls of radius eta. Now, if I'm looking at I'm going to suppose that the law of the two guys are, I want to compare basically the behavior of the curve gamma at p equal 1/2 and of the curve gamma which is slightly off-critical. Okay, both of them I know will hit, you know, at least eta to the minus 7/4 small balls of radius eta. Now, suppose that what happens to the curve gamma? So when the curve gamma, which is the sort of at p equal 1/2, when it hits the ball for the first time, roughly speaking, so I'm just, you know, waving my hands here, roughly speaking, because I'm at p equal 1/2, it will not turn more to the right than to the left inside this ball. Right? So roughly speaking, here it will behave, you know, like in a fairly symmetric way. So it will be sort of balanced between turning right and turning left here. And because what percolation in different balls are independent from each other, basically each time the orange curve hits a new ball, you know, it will toss a new independent coin fair coin to decide if it rather turns to the right or rather turns to the left, whatever you mean by turning to the right or to the left. Okay. Now, if you look at what, you may raise the question about, what happens to the near critical one. Well, we just said, the near critical one has slightly more blue hexagons than yellow ones, so it will tend to turn more to the right. In particular, when you discover a new territory, you will discover new cells, and so if they are blue, you will tend to turn more to the right. So the off-critical case, when P is slightly larger than 1/2, will turn more to the right. So how often, what's the sort of bias, the small infinitesimal bias, that tells you that if I discover a new cell, what's the probability that I'm going to turn right, or more right than the actual critical case? Well, in order to turn more right, what has to happen is that now I'm going to, this is the ball of radius eta. Right? And here I have my small mesh size delta, because everything corresponds to the scaling limit of what I see on the mesh delta. So here I have roughly, so this is a eta over delta cells. The radius in terms of the mesh size will be eta over delta. So what you need, so you arrive here, you hit this guy, and what you need, that the critical curve is going to continue like this. What you want is, what's the probability that my new thing, substantially turns substantially different than the critical guy? Well, for that to happen, what you need is that somewhere here, there is a site that has been flipped, that has become blue, and that was sort of pivotal on that scale. So you need here to have a site here which has the same picture as before, so that you have to go through here, and then this picture like this, where this was yellow and became blue. So in that sense, the orange curve that arrives here, will have to go out more to the right than the one which was the balanced one. So what's the probability that this will happen? Well, you're roughly saying, how many possible cells do I have here? Well, I just said that it's eta over delta to the -2. That's the number of cells I have in this, on the lattice, radius that's, in terms of the lattice size, I'm looking at a ball of radius eta over delta, so the number of guys is this. And then, what is the probability, what's the probability that that the given guy has a 4-arm time picture like this? This will be eta over delta to some power, which is this 5/4 that we had before, which is this 4-arm probability. And then now, I'm just pushing this off, by a factor p minus 1/2. So this is the number of candidates, if you want. And the probability that each of these candidates is actually flipped is p minus 1/2. And we just said that p minus 1/2 is delta to the 3/4. Okay? So what you end up here is that the probability that in a given ball of radius eta, the new curve turns more to the right, that you can see that it turns more to the right than to the left. Of course, the delta disappear, which is nice because you are looking at something which should be delta independent in the scaling limit when delta goes to 0, and you just are left with eta to the -3/4. Okay. So now what you are going to see, so of course, it's still, the first guy is like a simple random walk. Each time you discover one of these 1 over eta to the 7/4 little thing, you toss a coin to decide if you turn left or right. That's what happened when p equal 1/2. Now when p is not 1/2, but slightly off balance, what you are doing is you are tossing a coin, and the coin now will be, with turn right with probability this, because this was the probability that the first one turns right, and now we have a probability that you turn more right than the initial one, so the bias is that one. Something is wrong here. Well, sorry. is this. So everything is the other way around. Is that what you're saying? Yes. So, okay. So here we have a plus. Yeah, otherwise, if you have an infinite probability, we would be in bad shape. So the probability when eta is small, the probability to turn more to the right here at that level would be like 1/2, which is the standard guy, plus eta to the 3/4. So what we are doing now, in some sense, we are in the same situation as the one we were starting with. We have eta to the -7/4 attempt, because that's the number of times, number of little balls that you're going to visit. And now in each of the attempts, you have a small bias to turn to the right, which is of order eta to the 3/4. Right? So basically, if you look at this Sn, sort of, if you say +1 turning to the right, -1 turning to the left, and you add up everything up to these eta to the -7/4 guys, then in average, the difference between the number of right turns minus number of left turns will be eta to the -1, right? Because that you are that many attempts, and each time you have that drift. And if you have eta to the -7/4 attempts, and you are at equilibrium, right? The typical deviation between number of right turns and number of left turns will be, because of this central limit theorem I told you before, of order eta to the -7/8. It will be the square root of this guy. And so what you see here is quite clear, is that the accumulation of these little drifts here, even though the little drifts, the little effects tend to disappear, they don't disappear fast enough. So what is going on is still what we had in the one-dimensional case, so that you still have the picture that I have the off-critical gamma, which is not at p equal 1/2, and if I zoom in here, if I look at the picture and I blow this up, the p, that you are looking at here, in some sense, becomes more closer and closer to 1/2, exactly as the drift was disappearing in the Brownian case. So locally here, the effect of the asymmetry disappears, but it doesn't disappear fast enough so that in average, if you average along the entire curve, you will still see, an abnormal excess of right turns as opposed to the left turns, and you will be able to detect it. Okay. So this says that in some sense the real world interfaces, because as Pierre has been explaining, in actual sort of real phenomenon, you are never exactly at 1/2, right? That's the way the real world phenomena will always happen, the first time some crossing appears, and this always happens when you are actually off, in that regime where you're close to 1/2, but not exactly to 1/2. So this says that in some sense the real world interfaces are not exactly the SLE curves that we have here, but they are these type of guys which share exactly the same, exponent and so on than the one you get at critical values, which is nice because it means that what we did to study critical percolation at the critical value is useful, but they are not exactly the same random curves. You can still see sort of some sort of asymmetry there. So it just means that now if you go back here, you have this competition model, and they are going to create an interface that basically, usually, if one is very slightly stronger than the other, but not strong enough, to eat up everything, then the interface between the two will sort of remember it and will be slightly asymmetric. There will be another way to say will be, that in some sense, the fjords in one direction will be different than the other, or something. Okay, now I'm really. When did I start actually? Okay, so those of you who went at my lectures don't know it, but I tend to go over time. Okay, no, I will be very, very short now, sort of. Now, there is one very strange thing that has emerged in the. It's actually not true that I can go. I usually go over time. When I have 1 hour, I finish after 1 hour. But one very funny thing that has emerged here in the, and I'm going to state it in terms of percolation just for you. I'm going to forget about universality and Brownian motions, and I was planning to say something about the outer boundary of Brownian motions, the fact that off-critical Brownian motions were still Brownian motions, and that the boundaries of off-critical Brownian motion were still the same, and so on. But what I want to explain now is one very simple, funny thing. So imagine now that I'm looking basically at the interface between blue and yellow. Still the same picture. So as I told you, this orange thing is closing up fields. So the picture is really like that. You know, it's not really like you would imagine that, you know, blue and yellow are sharing territories in a smooth way, because in some way blue has, you know, little sort of yellow has yellow pieces, you know, that in some sense disconnect the blue pieces that are here. So when you have a picture like this, then there is one very natural thing to draw, which is to take, you know, let's just declare, you know, that when yellow invades, or when blue invades, but let's say, look, yellow invades this here and this, that it cuts out blue. So in some sense, what you're going to say is that, look at this curve, which is now, you know, the outer boundary of the orange curve. You know, that you don't allow blue. You'd say, well, blue is not, you know, is not able to make it through these little fields, actually. So you define the outer boundary of this orange curve, because this orange curve has double points, and you just look at the outer boundary of what you see here. Now, so here, of course, you are doing something non-symmetric, very heavily non-symmetric, because I take the outer boundary of the yellow one. Right? The outer boundary of the blue one would be somewhere here. And clearly, somehow, you would expect that if I look locally at the orange curve, at the red curve here, you know, because the definition itself of the red curve is very heavily non-symmetric. You know, it's, you know, white, you know, yellow is allowed to close up fields, and blue is not, right? That's so you break up sort of the global rule. So the law of the red curve is very heavily non-symmetric, but one of the things that comes out of this picture is that, in fact, the red curve, you know, if you look at it locally, becomes symmetric in the limit when delta goes to 0. So this red curve is a self-avoiding curve, and, you know, you have this cluster, you know, and you close up the loop, you know, you wrap around the cluster in a non-symmetric way, so that you wrap, you know, you are just looking at the outside hull of a cluster. So let me put it this way. You have, the claim I'm doing is the following. Maybe that's the simplest way to do this claim, but that's, imagine that you do percolation on a sphere. Okay? That you are doing this on a, or maybe better, let's have fun a little bit and do some baby Riemann surfaces. So imagine that you have a torus, right, which you represent as a square, so that what you see here is the same as, I mean, when you go out here, you come back here. When you go out here, you come back here, right? Like in our video games. Or, so, how is it called? Snake, the thing you play on Nokia telephone. Okay, anyway. So you are looking at that picture, and you do percolation there. You know? And you imagine that here you have you observe an orange cluster, so a set of orange sites that is connected to each other, and that is of that. So usually if you go around, the exterior of this thing, of course now exterior doesn't mean anything, but if you go around the outer boundary of this guy, as we said before, it will be a curve like before, except that it's a closed curve. The separation between a yellow cluster here and some blue cluster there. So that's the orange curve, if you want. And now you wrap around, just do this little asymmetric thing like this, right? So this is the outer boundary of the yellow one, and in terms of the blue one, it's some sort of inner boundary of the blue one, because you have a blue curve here, and you have cut out, all the fjords that went outwards in some sense you have cut out all the little balloons that were attached to the blue one. So very non-symmetric picture. Now the claim is, which comes out of this SLE analysis and which is a non-trivial, highly non-trivial claim, is that if I show you the law of this curve, you will not be able to tell if blue has been favored and allowed to eat up fjords, or if it was yellow. So in other words, if you draw this picture like this, you don't know if the yellow cluster was here and that you're taking the outer boundary of a yellow cluster, or if the yellow cluster was here and you were looking at the interior boundary of a yellow cluster. Right? So some symmetry emerges in the scaling limit, some symmetry that was absent in the discrete case emerges when you let the mesh of the latter go to 0 and you look at, things that are obtained when you wrap up stuff. And the same thing is true, for all these and for all these nearest neighbor models, actually, sort of that this type of, or conjecturally true, that this symmetry is going to emerge. Now the question is, what happens to these red guys when they become slightly off-critical? Now you can just say, well, you have wrapped up around the yellow path, and now you increase slightly P. Is this guy going to be sort of unbalanced or not? So it's quite clear, that the red guy here will be, okay, you can prove it has a dimension smaller than the other. It will be of dimension 4/3 in the scaling limit. So in other words, if you try to play the same game as we had before, instead of 7/4 guys, we will have 4/3 guys. Right? And, well, and then, this little game, which was comparing this with eta to the -1/2, here we were lucky that that 1 was larger than 7/8. When in the other case, the back of the envelope calculation tells you it doesn't work. So it's clear that you will not be able, to adapt directly this proof to prove that not only the yellow curve becomes different, but the other one becomes symmetric too. So, okay, maybe now I'm running out of time, so I should be careful not to disgust you by running too much out of time. If you were a physicist, you could produce an argument that tells that actually the red curve, or not an argument, or the argument I could produce could be accepted, as a physicist's argument that tells you that these outer boundaries, they are more stable. So the outer boundary of the off-critical guy still is absolutely continuous to the outer boundary of the symmetric guy. So that these simple self-avoiding curves, that appear, when you try to push them, they are more stable than the others. And in fact, in some sense, it's not so surprising because, okay, maybe I should just say one word about this. There are many different ways to construct this red guy. One way to construct the red guy would be to say, to take, a Brownian motion, two-dimensional Brownian motion, and to take the outer boundary of this, and the law of this outer boundary of a Brownian motion, which is also something very highly non-symmetric, is the same as the outer boundary of the percolation cluster. So we see that in some sense, these sort of laws of these special self-avoiding curves attract much more stuff, even non-symmetric stuff, than the ones that are much more convoluted. So now it's still an open question. So we don't know how to start the proof to prove that actually the law of the red guy, mathematically is absolutely continuous in the off-critical case than in the critical case. And of course, the reason is it's much easier to prove that two measures, are singular with respect to each other by just detecting something that they don't have in common. If you want to prove that two measures, and especially if one of the two you have a hard time is defined only implicitly by subsequential limits, to prove that they are, have the same support is much more, is in some sense harder. Or in some cases it's easier, but in that precise case it's harder to prove that the things are equal or absolutely continuous with respect to each other, because they cannot be actually equal. Than to prove that they are different. So the global message is the following, and which is, okay, that's, at the very beginning, okay, at the very beginning of my lectures, I make a very stupid joke about, because being recorded, is sometimes can inhibit, you saying stupid jokes and so on. And then I made this very, very stupid joke saying that, about American professors who have to entertain students, and so they are really trained to make more stupid jokes and in order to entertain the students. So now I have the feeling now I'm becoming an American professor during this lecture, and I made all sorts of hand-waving arguments in order to okay, anyway. So that's only for those who were here at my first lecture, who can understand what I mean. So the general message is the following, that there are two ways to define an interface in some sense, or to define between two domains. There are different ways. If on microscopic way, if this thing is going to lead to something like this orange curve, which is not a simple curve, right? Then in real life, what you will see is an orange curve that is very likely to be non-symmetric, even on infinitesimal scale, so that you will be able to detect, that blue and yellow had different strength, slightly different strength. If the way to define your interface, produces a simple curve like this, the self-avoiding curve, then this guy will be more stable, and these guys, you will not be, we'll still have a lot of much more symmetry, sort of a left-right, top-bottom symmetry. Now, I should emphasize that sort of these asymmetric guys, and this is sort of a highly non-trivial thing, in order to detect their asymmetry, you cannot just zoom into one point and see if what you see is different, because then if you zoom into one point, then you lose this asymmetry, this will disappear. So you have really to see a little piece of it and to average the behavior of gamma along a number that tends to infinity of small pieces in order to be able to detect this thing. So you really have to play this game with it, taking an infinite number of little balls and averaging something on these infinite number of little balls. And this is the reason why basically the finite dimensional distribution somehow of the law of the orange curve looks symmetric. But when you look when the number of little balls you look at tend to infinity, then maybe you see start seeing diverging features. Okay, so I will stop now, and thank you for your attention.